So, this morning's first talk is Machine Learning Engineering Principles with Python and MLFlow by Natu Lalchande, who works for Jumo World in Cape Town. Take it away.
Okay. Morning, everyone. My name is Natu, and I'll be talking around machine learning engineering principles with Python and MLFlow. It's basically a presentation around some research that I've done as part of the ML team at my company around different machine learning platforms and tools and approaches used out there in the industry, and trying to play around with some of the platforms that are out there to solve a couple of pain points that I will explain just in a bit. Yep. So I work for Jumo. It's a fintech company, and we use machine learning for financial products. So the agenda is around, it's basically, the talk is divided in 4 parts. We'll be talking about machine learning engineering pain points, or machine learning pain points in general. And we'll do a small survey, of a couple of best practices of some companies that have published their machine learning architectures online, like Uber, and we'll also look at some Databricks architectures and Airbnb, and I think Facebook as well. And we'll try to extract from this initial research a couple of principles and find ways to address some of the pain points, the normal pain points that data scientists complain about generally. And then I'll just show an example of usage of MLFlow in this context. So out of scope is a detailed review or specific algorithmic or data science solution, and it's definitely not a tutorial as well. So it's more a survey of tools and a set of notes, research notes, and recommendations on the ML engineering space. Cool. So starting with the context of machine learning these days, so it's kind of easily accessible. So everyone can do an online course and realize that knows machine learning and set up a Jupyter notebook and solve big problems and make a lot of money probably for their companies. But we generally know that the solutions generally don't scale, and there are a lot of issues with particular novice data scientists that just want to put their Jupyter notebooks into production. So generally things work very well in your development environment, in your machine. Oh yeah, you have this amazing 99% of accuracies, able to bring to the company $1 billion in revenue on your Jupyter notebook and things like that. So, but these things need to go into production, and when you just move them to production without proper code, like what we've found in the past from experience, it's just problems. So things don't work well, APIs don't scale correctly, so we went around and looked for a couple of tools. Another second important pain point is data entanglement. So basically, I don't know if it's clear here, definitely not clear. So data comes from everywhere, and there is no control over like data traceability or what type of data generated that particular model, or sometimes like what data is being used for scoring, if this data is the same as the data used for modeling. So this is a common pain point that the industry faces in general. Another important pain point is keeping tracking of your experiments in machine learning. So basically your models, and you do improvements, and you want to trace back and understand which parameter generate that amazing accuracy or the metrics that you want to optimize, or your log loss. And it's definitely very, it's not trivial to keep track of the context in order to reproduce your machine learning model for production. And also, like, it's very important to keep track of important metrics like underfitting and overfitting while you are doing model development. So this is also an important pinpoint. The question is, how do you handle these issues? So machine learning engineering might come into rescue is basically that intersection between back-end engineering, data science, and DevOps and data engineering. So different companies call this role different things. So in my own company, we generally call it data engineering, but we are morphing into machine learning engineering just to keep up to date with industry best practices. So basically, it's a practice or a role that understands a bit of backend, has information around continuous integration, deployments, and obviously data engineering, talking about your big data, how to manage data with Spark and Stream, Kafka, things like that, and obviously has some knowledge of data science, receives inputs from data scientist models to be deployed in production. So just to help build up the context of this process. So this is like an idealized workflow for machine learning. So you define your business problem, your context, you prototype, and on your left side is when you start moving things into production. So basically, the machine learning engineer starts collaborating basically from the final phases of prototyping when your model has proved itself to be reliable and potentially productionizable. And this is actually a Uber approach for the machine learning lifecycle. And these are kind of like the 4 different steps. So you define your problem, and from there, like the set of gates up to prototype where your data scientists actually try to prove the model. And then obviously production where you start having information like bringing up data engineers, machine learning engineers. And obviously, after this is in production, you need to close the loop and monitor and get insights from your model. Another context definition for machine learning engineering. So this is a very recent article around from Martin Fowler. I'll explain with a bit more detail a couple of things down the line. So it's trying to put the machine learning engineer in context of the machine learning life cycle. So when you receive a model and you need to deploy into production to extract value out of the model, and the data engineers, although it's a very small block, but it's actually probably the most complex block, is the block responsible for acquiring the data, preparing the data, and ensuring the data has quality to produce good models so the data scientist can move on. So this is also, again, giving a bit more context why we actually need machine learning engineering while deploying a machine learning system. This is a famous article by, I think, Dan Scully from Google Research. So as you guys can see, like the ML code is just a very small percentage of all this process. I actually had a lot of problems with data scientists in our company because they really didn't like this, because the rest of the work is basically for data engineers and machine learning engineers. So, but in reality, like creating the machine learning code is just, like on the machine learning system, developing the model is just a small part of the problem. So you actually have configuration. Obviously, this system needs to be configurable in some way if you're deploying in multiple locations. You need to do data collection, reliable data collection. Your pipelines need to work correctly. You need to generate features. And each of these squares have their own tools in general. And you also need to manage your infrastructure, like from a DevOps perspective. And you need to have a serving infrastructure, and obviously you need to monitor. Please feel free to ask any questions. Like I'm fine with questions here as well in the middle of the session. So after this, like a couple of principles after this, after some initial research on a couple of papers and a couple of architectures that we'll delve into a bit more detail soon. So one of the things that we have tried to extract was this machine learning engineering principles that we should try to look on the tooling or on the approaches for new projects. So one of the important takeaways from our initial research was taking this software engineering approach and a platform view of the ML functioning. So you produce the output of your ML functioning, obviously, if it goes through all the life cycles, if you discover that the model has value to give to production. Obviously, it's taking a software engineering approach to productionization phase and even for model development. So to aid the data scientists, you can create multiple tools to aid the model development process. Another important thing is to have reproducible and reliable model management. This is around what we talked about, the fact that like having traceability of models, which model worked and why, particularly these days around like when you need to understand a bit more why your machine learning models took specific decisions. So models are produced from data, and having this artifact that contains the data and the model in itself is critical to be able to trace back to the reason why your model is taking some decisions. Yeah, and actually data scientists, they really need like tooling and infrastructure to move fast. So these are kind of the guiding principles, the initial guiding principles that we extracted from this initial research and looking around for what was out in the industry. And now I'll delve into a couple of examples, and that will just stress the software engineering approach that's taken in the industry in general. So I spent a lot of time, not a lot of time, sometime, looking at a tool called Michelangelo from Uber. It's public and available online, so we looked at the papers and the blog articles and videos and things like that. Yeah, so this is the Uber approach to machine learning engineering and machine learning platforms. So they basically have like a pretty beefy software platform with multiple components. So this is all available online. If you Google for it, you can find the very same image. So basically, the idea of this platform is to serve their army of data scientists to rapidly productionize models and deploy models with less friction possible. Because in the end of the day, as you might know, like data science is a very fast iteration approach. You need to be able, a lot of models, like you can't actually figure out if they work just in dev. You need to put them out in the wild because this is the moment where you have like real data. So this platform enables Uber to actually rapidly deploy models, and more than anything, like it's highly scalable, as you can see from the different components. So I'll start with the general approach. So they have like an online and an offline approach, and an offline component. The offline component, it's where your model training happens, your data preparation of batch data happens. And the online approach is when you want to serve your model. So basically the first step is acquiring the data. So the data can be from Kafka or from a data, like on the online approach, basically most of the times we will be talking about kind of real-time systems or event-based systems where you can get events from your, let's say, ride-sharing app, like requesting a ride or canceling a ride. So these events do come in real time, and they send these events to the stream engine. So on the stream engine, they actually try to implement a lot of the business logic around the feature generation. And there is like an important problem in machine learning. So you need to be able to do the same processing that you do with your training data, with your inference data. So what they do to solve that problem is that they have this beautiful V in here, is they double write, their business logic is in here, and they double write the logic to a feature store, that is accessible in real time, and they're more slow, kind of like big data world or data warehouse in the current world. So in that way, so the logic is only in one place, but you still can serve in real time and still recover that data. So that's the online in terms of so regarding the get data component, so they basically have a data lake. Data lake is just a fancy name, I think, these days for data warehousing. So where all the data of the company lands in a way that is accessible to different data processing jobs. So the data lake contains most likely the metadata, data quality assurance, and after the and feature generation as well. So from there it goes to the Hive feature for the Hive version of Feature Store. So it's basically a Hadoop front-end database, and and that's basically it. And they also collect the outcomes of the training process and a sample of predictions. So the second stage is training models. So basically, these models are training in batch with different training algorithms, and they have a model repository where they evaluate the best models, and actually it's basically an object store that can, after that, deploy the models in two different places, because as you guys might know, there are two approaches to predictions in machine learning, like you either doing like real-time scoring or batch scoring. So batch scoring generally happens with tools like Spark and Flink and a couple of other big data kind of tools. And on real time is generally fronted, all this is fronted by APIs. So, but the same model is deployed in both cases. And most of these services, like the real-time prediction service, it's written once. You as a data scientist, you don't need to rewrite it. So your output is your model, and your model is packaged and from engineering and deployed. So this was kind of like, And after that, you as a client, when you are requesting a ride, for instance, and trying to predict like how much time it will take from your mobile phone and your location and things like that, the features go directly to the prediction service. And at this point, the prediction service also makes the correct call to the feature store. So this feature store is also like generally backed by DSLs, and it's very easy to access them from the model. And so this is the prediction component in real time. And in batch is very similar, and after that, the predictions go to Hive or Kafka, and there's a monitoring block here, sorry. Oh, sorry. Take this out. Okay, no problems. So this was the first version of Michelangelo, but there was like recently, so that first version had a small problem. So most of the work was done by engineering. So the data scientists would provide models or notebooks to engineers, and engineers would like deploy this system into their continuous deployment pipelines into the platform. So they noticed a couple of problems that probably a lot of companies have noticed it, that like having this cycle not in control in the data science can be a friction point. And what they tried to do with a tool called PyML, I think it has at most like 1 year or 2 years, 1 year and a half, is actually giving the power to the data scientists. So basically, from your normal Python tool, you can instrument deployment into Docker containers or and into prediction services directly. So this is, so there's last point is like just going a bit on detail on the Uber feature store. It's also another important component. So they basically have a spec for features. The idea is that multiple teams in the same company can actually have like a central location for a feature that's relevant and predictive, and you can keep metadata around prediction power of that feature, so and make it discoverable as well. So I'll be very quickly on this one. This is I think one of taken from a Facebook blog. So they have a platform that has similar functionalities in general. So it's always the platform approach to accelerate data science and machine learning systems. So there's also another interesting one from Airbnb. So very similar tools. You have a feature store, you have your big data component, and you have also prediction services. And obviously, since they are the owners of Airflow, the creators of Airflow, there's a lot on Airflow and workflow orchestration in here. So, and this is a simple machine learning platforms comparison from Microsoft. So they did a bunch of comparisons on different open source tools. And so one of the things that you can notice is the majority of the non-proprietary tools don't have the most important part, it's data management. So that was also an interesting point to me. And yeah, that's the summary of the survey of the different platforms from big companies. There are much more survey platforms, but they kind of work in the same way. So since one of the principles was using software engineering principles and productionization is creating this life cycle, so one of the recent suggestions is something called continuous delivery for ML. So it's basically creating a pipeline from model building and evaluation and experimentation, but everything in your continuous deployment environment if you are making your, let's say, the model discovery or refitting your model with new parameters as part of your pipeline end-to-end. So one of the important things that you need to do is testing everywhere. So for instance, let me just go back. So for instance, you have to test, for instance, the output of each of the systems, of your model, of your productionized model. And obviously your deployment, you still need to use normal software engineering principles with canary testing, integration testing, and smoke testing. So bringing all this machine learning, software engineering practices of the last 20 years into this new machine learning world is critical for extracting value and being able to make the systems work. So this is another paper from the same team of the hidden technical debt. It's just basically a rubric for scoring machine learning systems, so it can help you improve your systems. So regarding the data, I'll start now with talking a bit about some tools. So tools that you can use for data lifecycle. So Delta Lake is an interesting tool from Databricks that you can actually version your data and treat your data in some way a bit like code, because it will be versioned by every time you make a change, it just creates a new version, and you can actually track that version to your models as well. So DVC is also a very known tool for that particular problem. If you want to make sure that if you want to test the data, there's some new interesting tools. DQ is from Amazon, so it allows you to test at scale, assertions around data distributions, and either from training data or from prediction data. And also Great Expectations, a fantastic Python library as well that can be used to make these assertions in your machine learning pipelines, either in code or in your CI/CD pipeline. There's a free, kind of a very recent open source feature store, similar to Palette from Uber, with the same ideas. It's called Feast. It's from a company called Gojek as well, but it works in a similar way than Palette from Uber feature store works. So I'll go to the main topic. So I'll have to extend a bit because I start a bit late. So what is MLFlow? So MLFlow helps you in specific components of your machine learning pipeline. So the three important things that I would say is experimentation management, reproducibility, running your systems or your models versioned, and you are able to run them at the same time, and standardization of ML projects, and potentially standardization of deployment operations. So from the same packaging system, you can deploy into Kubernetes, SageMaker, Azure ML, and Google Cloud, for instance. So it's kind of like instrumentation around your machine learning system. So what are the most important MLflow components? So there is an MLflow tracking. Basically, it's a module that record and query experiments, code, data, and configuration, and results. So while you're developing, even if you're developing in your notebook, you can start logging your models, logging your data. You can log a hash of the data or the data in itself if it's small data, and configuration and results. So at that point, it's basically a closure of all your ML system at that moment. It's versioned, and you can use like whenever you want, and you can package it and make it available for deployment and in different systems. So there's the MLflow projects component. It's basically the package standardization, and it's an important component. And MLflow models, it's the deployment component based on the fact that your project is standardized. So there are multiple flavors of MLflow models, so you can decide, and the MLflow takes care of the abstraction of deploying on the service that's more convenient to you, either Spark, either REST API, or Azure ML. All of this is open source in Python. You can inspect the code, but it's actually like something that allows you to go faster to production. This is a very complex pipeline I'll share with the slides as well. So it contains all the components and how would you use MLflow and a lot of the tools that we spoke about to do important things like drift detection, monitor your models, and deployment scoring, and model your pipelines. Yeah, there won't be a demo, but anyway. So I have a GitHub package that I've been playing around in the last couple of weeks with toy examples. The topic is really not very relevant, but it was just fun because we can have data coming all the time. So it's basically trying to predict Bitcoin price. Very easy. It's always going down. So, so this is the toy example that I'll show you, like, and how to basically use MLflow for this particular example. So you have an ML project, and you can go and look at the repo now. So this is like the toy example. Like you just specified the name of the project. You specify the environment. You can actually have Docker or, yeah, I think you can do it as a packaging. It can be Anaconda or Docker. And you can also have like entry points. You can actually orchestrate a very complex pipeline on this component. And this is your standard conda file. If your packaging strategy was Docker, you would have like to have your Docker file. So I basically use here Python, scikit-learn, MLflow as well, pandas and data reader. So when you save your model, it also saves with these dependencies, whatever is the version of your model that you used. And there will always also be a GitHub repo hash that you can always go back to that specific version. And this is like a very simple pipeline. Sorry. So you basically train your data, you acquire your training data. You just have to make sure that you are using the with MLflow start run. So MLflow struts and enters down. So you acquire training data, you prepare training data, and there's some code to just do some feature transformation in here. And you have like a classifier, like the random forest classifier. And you fit your model, you predict, and then the most important part is you log your model. So with this logging of your model, it will log the pickle of your model automatically, depending on the format. If you're using TensorFlow, PyTorch, or sklearn in this case, it will persist in the correct way that it can be loaded automatically. So with this, just with this piece of code, all the deployment mechanisms are available to you. So I'll show you probably, how does it work? So if you do a run, it will just execute training and log your experiment and create a new model with all the dependencies available to you. And at the same time, so this is how the MLflow infrastructure looks like. It's just a UI where you can have your metrics and you can compare. It's pretty cool. So you can actually inspect each run of your system. Each run of your system, there's a run ID, there's a git commit, so you can go back to the specific code point. I'll use some minutes from the questions. Thank you. So yeah, the source, duration, entry point, what's the command that you run, that exact version. Every time that you run, it creates a new version with dependencies and things like that, and you can compare all your metrics, and you have artifacts in here. What's this? Okay, so explain the artifacts. The artifacts are basically your model, your dependencies, your Docker file, everything that allows the system to run it independently, that particular version of your model. So just with that few lines of code and a few configuration, you now have an API that you can actually use for an MVP in a production system. And you basically, because like the smartness of MLFlow is actually transforming your code that will be in, for instance, in a notebook, or it can be actually in code, like you have already logged the model, so it's available for the prediction service to serve it correctly. In order to serve, you just need to run this command, and you have a REST API that you can call directly, and it will give you a result that you can use in your application. So it's a very fast way to iterate for data scientists. So if they really want to, from day one, they can have an API that it's a model, it can be deployed with some infrastructure still, but it can be easily testable, and like if the model actually is profitable and makes sense for the company, then like more work can be done. And in the same way, you can do champion challenging with this approach, because since you have like all the tagging, and you can actually run two models at the same time and test and log the metrics and see which of them is better and decide. So the last part is how would you do predictions monitoring? So it's very simple. So you have your runtime. So you log your model, MLFlow, you load your model from MLFlow, you predict, and you log predictions in Delta Lake. Delta Lake is just like a data lake, the data lake tool, and you can compare and you can monitor drift and alert with your normal like Elasticsearch and Grafana tools. So this is an example of a dashboard of predictions. So with alerts and probably PagerDuty if it makes sense. And I'll forget about this example, but it's again another example in the NLP section, but I don't think we have time. Cool. So there's more time?
There was a delay somewhere else. So
Okay, cool. Okay, so this is another example of a project that I've done, and I've used MLFlow. It was just like a collaborative project in an organization called Omden, and we were trying to do a text classifier for to assess risk of PTSD. It's a complex story, but basically there's a chatbot, and there is like a set of the dialogue of the text. And one of the challenges that we had in that is that we had 35 engineers writing machine learning models, and we needed to do it in a quick way, in a way that we could just verify what was the best model. So one of the tools that we used for that project was actually MLFlow to actually assess the best model and use the best model in the end. So it's also like very simple. So here you have a very, like this is an example of one of the models. So you have a very simple pipeline that does TF-IDE with text, and it has a logistic regression. So the cool thing here is because you log the pipeline, so the data transformation is already embodied on your API call automatically. So there's a lot of magic here. It's impressive. So yeah, and you just need like 5 lines of code to put your model, to actually log your model and deploy. And this is like the platform that we use to try to find the best models. And this is again the tracking and versioning part that we discussed. And this is the serving layer as well again. And you can choose multiple backends. You can do it in batch with Spark, or in this case as a REST API. And this is an example of a call. And you just basically the call format here is the pandas data frame. So you just wire a pandas data frame in JSON format. So because you loaded the pipeline, it's able to do the transformation for you for free without doing any code. And yeah, it can be deployed and tested and integrated with many systems. So summary-wise, from all this research and playing around for these tools for the last year, so it's still painful to move from development to production, but these tools do promise a lot. And I've used in a couple of circumstances that the tools like that I mentioned were useful. So the ML ecosystem is very recent, as everyone knows, and frameworks are still maturing. So a lot of these frameworks are not even version or version 1 something or before version 1. So we need to be patient and send pull requests as well. DevOps and standard software engineering practices are like the key to get value out of these systems at large scale. And one important thing is having cross-functional teams working on ML projects at the same time is also one extremely valuable thing. So you can have data scientists and production engineers in the same boat. That is basically it. So that's basically it. Questions?
Thank you very much. The following talk has been delayed to 11:50. It's now starting at 11:50. And the schedule change has now been updated on the website, so please refresh if you want to see what the changes are. And now we have time for a couple of questions. We need someone, a second person with the second microphone maybe, on this side of the room. So please put up your hand if you have a question. Wait for the microphone and speak directly into the microphone, not... hear you.
Hi, thanks for your talk. With regards to like data management and model management and stuff, during that experimentation phase, where you're iterating through different model architectures and hyperparameters, does MLflow cater for the storage of metrics in the sense of, like, let's say you have multiple confusion matrices per experiment that you've run? Is that something that's also catered for?
Yeah, so at the same time, you can log multiple models. So the concept there is kind of an abstract concept, is an artifact. So within an artifact, a type of an artifact is a model, and you can have multiple artifacts logged for one exact run, and multiple metrics associated to each artifact, so you can compare. And you can log also random reports, including confusion matrix and things like that.
Okay, awesome, thanks.
We have time for other questions. Gentleman here.
Hi, thanks. Congratulations, awesome talk. You went very quickly over that section where you showed the actual code.
Sorry? Sure. Which code?
So there was like initially where you showed like how you define which metrics to log and so on. I think it was the very first example of code.
Okay, cool,
maybe
sure.
that one. So what other like in the MLflow package? I mean, like what other? So you've got sklearn there, but like what other maybe machine learning libraries?
TensorFlow, PyTorch. I don't remember from the top of my head, but the most important one. So ONNX and PMMLs as well. So basically the standard ones that you have, that you would expect, and you should be able to log. And you can also log your own as well, like if they're pickled, but the problem is that it won't give you all the benefits, or you'll have to write the classes. But the standard ones that you used in machine learning in production, let's say 80% of them, like PMML, ONNX, TensorFlow, PyTorch, and Keras, obviously, and
yeah, they're all covered. And then apart from the functions that you showed there, like the log metric, is there other like rich functionality?
Log artifacts, log artifacts, log parameters. So all of these things are handled in a different way.
Okay.
But awesome. I think for me, the brilliant function is the log model in some way, because it logs your model, like the binary of your model, and your dependencies at the same time, including your GitHub details and your exactly hash commit as well.
Okay, awesome. Thanks so much.
Yeah.
And we can do another question.
Hi there. So I prefer to learn from other people's mistakes without making them on my own. So I was wondering, what was the biggest mistake you guys made during this whole journey of productionalizing your ML models?
Biggest mistake?
Yes.
Sure.
The one I shouldn't be making.
I think not having monitoring, just deploying your models and expecting for the best. I think this is probably the most important thing, because these things don't behave as you expect if you don't look at them. So I think monitoring is probably the first mistake that we have all made.
And one more.
Hello. Hello. There we go. How long does it take to train one of these? How long does it take to train?
It all depends on the data that you have. So it's very, like, so this, like, these examples are very are very fast, but like the one involving data, text data, because I had 1,000 examples, would take like 20 minutes. But it takes a lot of time, and it all depends on your infrastructure. It doesn't do anything smart. It's just a smart collection of existing libraries.
Okay, and well, what is the most complicated one you've created?
Yeah, I think none of them are very complicated. I think probably the NLP one, because we had to do it with UML fit as well, and that was quite hard because it was not provided. So FastAI is one type of models that's not available straight on, and we had to do a lot of coding to make it available in the...
And I think we can squeeze in one more question. Anyone?
Yeah, so thank you for your talk. This is very useful just to get my ideas going and like get us exposed to this. What I want to know though is, this is one, you've shown us how you can interact with the API. What I want to know is, firstly, I want to know how many of these have you actually implemented, all right?
Oh, hard question.
And then the second question always with this is, once you've exposed the API, you almost want to use that data in your next set of training data, you know? So we want to get feedback from it, and I want to know how you incorporated that in the process.
Okay.
So a lot about just the productionization of it, you know, because this is great to test something out, but my question is always when you get a developer in to come and productionize it now. That's when the trouble starts, you know.
Yeah, and I don't think the trouble actually ends. So basically, like you'll be calling it from a context. So within this context, you can always log it, like the result of your prediction. That's one approach. So it will be called either from the command line, and you can log exactly the prediction and the feature set that you used, and it becomes like a table somewhere else that you can... So it's built into the... Yeah, you need to build in. No, this part you need to code, because this is your own code. It's how you use the system. So like, yeah, monitoring is still lacking. Like you need to write it like by itself. Or use existing tools like
How many have you implemented? How big is that?
Yeah, this is very recent. So the one that I've used in a real project was actually the NLP example, but there are a couple of projects ongoing in the company. So one is the answer, but it's being used in the industry. Yeah.
Okay, that's all the questions we have time for. It's time to go to the next session. Yeah, so please check the schedule for the schedule changes, and next talk starts at 11:50.